right, so we continue with our discussion for the active filters. And this time we are trying to see another circuit. It's called as differentiator. So we realize this circuit using operational amplifier. So let's draw the schematic. What we see here is the circuit of operational amplifier integrator. We've seen that in the previous model where output of this circuit is given by 1 over RC integration of input signal, that is Vn of t. Okay. So of course this is with respect to time. And now what we do, we swap the position of the capacitors and the resistors in the circuit to obtain this new form of a circuit. So we have this capacitor here, and in the feedback, we apply a resistor. And we again have the same notion, Vi of t, or rather, let's say V in of t. So how to analyze this circuit? So again, the node voltage here is V2, the node voltage here is V1, and operational amplifier, job of the operational amplifier is to amplify the difference between these two signals. So we know that through the virtual ground concept, V2 is equal to V1, that is equal to 0 volt. Fine. So the current that flows through the capacitor indicated by IC that charges the capacitor and produces a voltage across it. So it is called as IC. No current can enter the operational amplifier through its terminals indicated by negative and positive sign. So this current trying to enter inside the op-amp is 0. That's why we say that op-amp has infinite input impedance or input resistance. And therefore, the current that flows through the feedback resistor is, let's say, I. So IC is equal to I. So we can say that is equal to I. Fine here. And the current through the capacitor can be written as C, derivative of voltage across it. So voltage across the capacitor is dV in. So derivative of this voltage is the current through the capacitor. And that current can be equated to the output current I that flows through the feedback resistor, so which is minus VO over R. So therefore, VO can be written as minus RC derivative of VI by dt. So that is the expression for this circuit. So you see here, this is the expression for the output, which is the integration of the input signal. Here is the output voltage, which is the derivative of the input signal. So we call this circuit performing the action of differentiation. It performs the derivative action, differentiator. Okay. So in the S domain, we always know that let's write this equation, VO of t is equal to minus RC dV in of t divided by dt. So in the S domain, where we know that x is the complex variable, and we will explore more when we'll study the control system with this. So in the S domain, we see that VO of S divided by VI of S, which is the transfer function. We take this V in to the left hand side. It could be written as minus R C S. So here we see that S is nothing but d by dt. So here is how we get that. Now we put S equal to j omega to obtain the magnitude and the phase. So we can write here that VO of j omega, Vi of j omega, that's our minus j omega, as is j omega, RC. So that's the final expression for the transfer function. We can obtain the magnitude which is simply omega RC.